my lectures are going to be an introduction to the renormalization group from a mathematical perspective. And this is a vast topic whose history spans at least 50 to 70 years. So inevitably, I'm going to have to make compromises. And I'll try to do my best to make these lectures both accessible to those who have not had any contact with this subject at all, and to say something interesting for those who know a lot about the subject. And as you can see, there's going to be some tension between these things. I'm not going to give a big historical perspective, but I need to say a few words, I think. So let me begin with that. So this is lecture 1, and I'm going to try to say what the renormalization group is, or what the term means. And there's various places one could start, but I think the easiest one is to start with what's called Kardanov's block spin picture. So this picture is a kind of idealized version of what the renormalization group is supposed to be. So this was introduced by Kardanov in the 60s, I guess. And let me first say what kind of problems the renormalization group is concerned with. It's concerned with problems where, let's say, they can be different, they can apply to different problems, but let's keep problems of statistical physics in mind. And the kind of problems it applies to are those where correlations or dependence over long distances remains important. So this is different from situations, say, the hydrodynamic one, where sort of interparticle fluctuations are known to essentially decouple from the sort of macroscopic equations of fluid dynamics. And a simple, or perhaps the simplest or most concrete example one can think of would be an Ising model at a critical point. So let me draw a box which is idealization for physical space. And we consider 2 points, say X and Y. And the situations where the renormalization group is relevant is when there are strong correlations between these 2 points. So what does this mean in the case of an Ising model? Well, in the Ising model, say we have a microscopic collection of so-called spins at, say, sites of, in this case, a 2-dimensional lattice. And one can measure how correlations, for example, by considering what are called the correlation functions. In the case of the Ising model, one can take the expectation with respect to the Ising model of the product of 2 spins at sites X and Y. And it turns out that at its critical temperature, these behave like a power law. So that's a prototypical situation where the renormalization group picture is relevant. There's a strong influence between these 2 points. Now, what is Kardanov's block spin picture about? Well, it's the simple idea that one might imagine the whole space as divided into blocks, say like this. And instead of looking at the interaction of individual spins in this case, the idea is that one takes some kind of average of spins over a block. Whoops, this was that's the so-called block spin. There'd be different ways to do this. And sort of the heuristic picture is that, well, in terms of, so each block has sort of an effective spin, and the heuristic picture, or the sort of ad hoc assumption of this block spin picture, is that each block more or less behaves like an Ising spin again. And then this is consistent. So in the block spin procedure is going from the microscopic spins to the block spins. And you could iterate this procedure. And that's what's called, what we call the renormalization group. It's an idealized picture because if you try to write down any reasonable way to go from microscopic spins to block spins, you'll soon realize that you get a huge mess. The microscopic Ising model looks extremely simple to write down. Once you write down, once you try to write down, well, a formulation how to go to block spins and how these interact, you'll see that they interact in a very complicated way. And this procedure, as nice as the picture is, it's infeasible calculation. Okay, so this is the block spin picture. There's a second historical motivation for the renormalization group, and that doesn't have to do with statistical physics, but it goes back to quantum field theory. And in quantum field theory, so this is, I guess, in the 50s, and the names that are typically cited in this context are Stückelberg and Petermann and Gell-Mann-Low. And it has to do with the famous, or perhaps I should say infamous, infinities or divergencies that were found to appear when trying to make sense of, say, quantum electrodynamics. It was realized that the couplet, or the effective mass or charge of an electron that one measures doesn't coincide with the microscopic guess you put into the description of the model, and in fact that the discrepancy between these was by an infinite amount. This goes back earlier to the beginnings of quantum mechanics, I guess. But it was realized in the 50s that there's some arbitrariness in the choice of these effective measurable quantities, which in some sense depend on scale and the microscopic divergent parameters you put into the model. So I will just, I will not say much about this at this point, but let me just write divergence. Let me just record divergencies and scale dependence of coupling constants. In quantum field theory. And I think the appropriate list of years to cite here would be the 50s. And it turns out that these two problems have the same root, or they can be regarded as two different aspects of basically the same question. And I think this was really understood conceptually deeply by Ken Wilson, in maybe I think in the late 60s and early 70s. There are also many contributions of others, but if one person has to be singled out, it would be Wilson in this context. But maybe a few other names to mention would be maybe Michael Fisher and Wegner and others. And let me, to lighten these lectures a little bit, let me put a picture of this is I think this is the picture from the Nobel Prize website they used for Wilson when he was awarded the Nobel Prize for these discoveries. I like the following quote. How he this is in one of the earlier papers on the subject. Whoops. I like the quote, how he described the block spin picture. That's this one. In short, the Kardanov block spin picture, or block picture, although absorbed, will be the basis for generalizations which are not absorbed. And in some sense, what he and others understood is a precise computational way how to understand this seemingly completely intractable block spin picture. It's a computational, and also conceptually, these are perhaps really two different aspects of the subject. One is how to actually understand this picture in a computational way so that you can do something. The other one is the broader conceptual picture that came along with it. So it's a computational and conceptual well, picture approach. Okay, so this is sort of, let me leave it at this for maybe the historical perspective on, or the historical perspective on the renormalization group. At this point, there's a few words I should say, which is that the kind of ideas I've presented here, they're extremely general. You might imagine this kind of approach of sort of this block spin approach, or something that sort of should capture the same features, would apply to a vast range of problems. It turns out it's not so easy to apply it to a vast range of problems, but I think there's little doubt about it that many of the problems that we don't understand well would fall into this category. The class of problems where it's quite well developed and reasonably well understood, even though there's much to be done, is those which I will call spin models or spin systems, which include the ones that are the perhaps historical first ones, the ones that are shown on this page. So spin models include, say, the Ising model, but I'll also interpret this term in a sufficiently general way that these models of quantum field theory are examples of this. So let me briefly tell you what I'm planning to do in these 4 lectures. So in the first lecture, which is today, I'll discuss the class of spin models. And in particular, I'll discuss the kind of models and regimes where the renormalization group approach is relevant. And that can happen, as in the example of the Ising model I showed, at a critical temperature, but it can also happen in phases of low temperature or high temperature, depending on the model. And I will give some examples of this. So that's part of, that's the first half. And then I will discuss and introduce sort of the main protagonist in the study of the renormalization group, which is what is called the renormalized potential. And I will focus in this lecture on sort of structural aspects of it. Hopefully I will convince you that it has, the renormalized potential has a beautiful structure, and understanding it is sort of can be well. I will hopefully convince you that understanding the renormalized potential is sort of a worthy goal, and the remainder of the lectures will be focused on how to do this. Now, how is this done? Well, a major source of inspiration and also a guideline of how to do this is based on perturbation theory. And I have to say a little bit about this. So I'll say how perturbation theory is done, and as simply as I can, without going into a lot of details, but to enough details so that I can convey what it does, and also, and perhaps more importantly, what its problems are. And I would say there are 3 problems with it. Um, and I'll try to explain this. Roughly speaking, the three problems can be described as that. The first one is that perturbation theory is the one of the infinities. If you want, perturbation theory has to be renormalized. The second one is what is known as the infamous large field problem. And the third one is what I would maybe call the infinite volume problem. And I'll try to explain what these difficulties are. So maybe difficulties is better than problems, but anyway. And I'll then show you how one of these problems goes away, namely the maybe most serious of these, but technically most serious of these, the so-called large field problem, when working with fermionic or Grassmann variables. And this does apply to a number of interesting problems, and I'll explain how this problem goes away there. And I think this is instructive also more generally. In the third lecture, my plan is to introduce what is called the finite range approach to the renormalization group. This is one of different different approaches to essentially deal with another of the problems that I'll highlight in my second lecture, which is that of the infinite volume problem. And I will explain this in the third lecture, or at least that's the plan. And likely I'll not, the third lecture will not be enough, so this will probably also occupy quite a significant part, or at least part of the fourth lecture. But I'll make sure that there will be time, and this will be the most technical part of these lectures. But in the fourth lecture, there will hopefully also be some time to to discuss a few softer aspects towards the end. And I will try to do this in terms of an example where I can illustrate various further aspects such as symmetry. And I'll do this in the example of the zero-state Potts model. Okay, I have, I'll put up the notes I'm writing here, as well as further references for a lot of things that I'll mention, but not discuss in detail on this following website. And I'll also try to compile a more comprehensive bibliography than those references that I can discuss in these lectures in person. And okay, so so much for the introduction. So the next item, my agenda is to begin with the class of models that I will focus on, which are the spin models and the regimes of their parameters where the renormalization group is relevant. Okay, so what do I understand as a spin system? Where we fix an underlying graph or lattice, which we'll always think of as a subset of ZD. For technical reasons, I'll always assume that lambda is finite, but it will always be understood that lambda is essentially infinite as well, in the sense that we're interested in understanding what happens in the limit as lambda goes to infinity. And alternatively, we can also consider the case where lambda is the subset of a rescaled lattice, epsilon ZD. And in this case, it will be understood that we're looking at the limit at everything uniform in epsilon as epsilon goes to 0. So that's the situation of quantum field theory. The first one is more the situation of statistical mechanics, but they live on this conceptually the same setting. Then we have spins. I usually denote these by phi x, but sometimes sigma and other variables will appear as well. So there's one for each site in lambda. And these could be, these could be, in the simplest instance, you can think of these as, say, Ising variables plus minus 1, or real variables, but they could also be vector valued. Its components could be, as I said, discrete, continuous, and or anti-commuting, and I'll say more about this later. So this is what I would be calling a spin. And then there is some kind of a statistical average associated to a spin system. And I'll use the term expectation, and roughly speaking, these systems take the form that the expectation of some observable f, say f is a function, for example, on r to the lambda to r, so a function of spin configurations. So there's a statistical average associated, which is roughly speaking takes the following form. We're integrating over f of phi with respect to a certain weight, and the weight usually has two parts. And I'll write this like this, where the first term you can think of as the, in this case, a discretized Dirichlet energy, where I'm summing over neighboring sites in the lattice. So there's so lambda is some kind of lattice, and we're summing x tilde y means we're summing over neighboring sites, x and y. And the first term is roughly this Dirichlet energy, and the second term is usually local, in the sense that it's the sum over spin sites of some local potential Vx of phi only at x. So that's roughly the class of models of spin systems and their various decorations and variations of this. And this is a class of models for which that, as I mentioned, both historically the renormalization group approach was developed, and also where really its understanding is most complete. And so I already mentioned that the renormalization group approach would be relevant for such models at the critical temperature. Let me say a little bit more precisely. So for example, if you're looking at an Ising model, well, that would be defined, say, in some parameter, in terms of some parameter beta greater than 0, which is called the inverse temperature, and then in this case, the statistical average would be given by summing over all spin configurations sigma, which in plus minus 1 to the lambda, and then taking the Dirichlet energy term, which in this case is just the exponential time of beta times the number of pairs of disagreeing spins. That's exactly what this reduces to. In this case, there's no potential term. That potential term is effectively replaced by the constraints that the spins take plus minus 1. So in this case, well, so spin configuration may look like this. Okay. And well, in this case, we know very well how these models behave, at least qualitatively, that there's a critical value of beta such that for beta below this value, configurations will look disordered. For beta above this temperature, or above this inverse temperature, they will look ordered. So roughly speaking, most spins have the same sign, the ordered phase, and there's roughly, well, they look sort of like independent coin flips in the disordered phase. And then there's the critical temperature in between. And this is where the renormalization group picture is relevant. And for these models, where in some cases we know, in other cases we expect that spin-spin correlations decay according to a power law. Okay, so now it turns out that you can also look at models that are, from a physical perspective, essentially equivalent to an Ising model, but that are of interest for various reasons. Not only its relations to field theory, which is the continuous versions of an Ising model, and that's called the Ginzburg-Landau or phi-4 model. And in this case, there are two parameters. One, G is going to be fixed, and then there's another parameter which will take the role of inverse or of temperature, which I denote by nu. It takes real values, and then the expectation of the phi-4 model is given in terms of these two parameters. As follows, in this case, spin configurations are real valued, so integrating over r to the lambda. There's again the same Dirichlet energy term, except I'm not putting a parameter beta in front of it, and that can always, since the spins are continuous, you can always scale it out and put it into the following two coupling constants, there's a term g phi to the 4, and there's another term nu phi squared. So this is the phi-4 model, and it in many ways behaves exactly like an Ising model. So mostly interested in the case where nu is negative, so that the potential looks like a double well. And in this case, what happens if nu is sufficiently negative so that it looks like a deep double well? Again, configurations are ordered. If nu is bigger than nu c, they're disordered. And again, at the critical value, we expect the power law. And the power law would, and here's one of the striking features that in some sense the renormalization group picture predicts, is that the power law is identical to the one of the Ising model with the same exponent. Now, I guess this is again a good opportunity to lighten the discussion a bit by putting a picture, and let me say that the pictures I'm putting are somewhat arbitrary. Those who get included and don't get included depends a bit on luck. But in this case, it's well, it's a good opportunity to. Let me try to move it down a bit. Well, it wants to go up. Anyway, let's leave it there. So these are Christoph Gewetsky, who sadly passed away recently. And Antti Kupiainen. And I understand Christoph Gewetsky spent a significant amount of time at IHES, so it seems like a good opportunity to emphasize his contributions to the subject, which are significant. And so Gewetsky and Kupiainen were, I think, the first or one of the first who were able to make this sort of this Wilson picture precise for these kind of critical phi-4 models, and later for many other models as well. And in that sense, their work plays an important historical role in the subject. Let me maybe, before going to the next class of models of interest, I should maybe say that, I've already mentioned that this parameter alpha, or this exponent alpha we expect here, would be the same for the Ising and the phi-4 model. In some sense, this is heuristically explained by the renormalization group. I'll get there in some to a certain extent later on. One would say this is there in the same universality class. Which is that of Z2 symmetry. There are many other interesting universality classes. Obtained, roughly speaking, by replacing the group Z2 by other groups. So, for example, there are the Potts models where Z2 gets replaced by the symmetric group Sn, or the On models, or classical Heisenberg models, and others. And this leads naturally to the next example I want to consider, which are the relevance of the renormalization group picture, not only for critical models, but also for, and one might say, perhaps even more interesting, for systems at low temperature. So, for low temperature, one might have the prototypical in mind is a classical Heisenberg model. So it's defined exactly as like the Ising model, except that the spins don't take values plus minus 1, but they take values in a sphere. It's defined exactly like the Ising model, except so for the Heisenberg On model, they take values in the sphere of dimension n minus 1, which we imagine as embedded in Rn, and then the measure is defined exactly the same way. So here, this measure product over sigma x is the Haar measure on rotationally invariant measure. So these classical Heisenberg models, at least in dimension, so dimension 2 is a whole different story I'm not going to get into here, but in dimension 3 and higher, they are again, like the Ising model, disordered for high temperatures, so beta small. and ordered for beta large. Now, it turns out this ordered phase is much more subtle and interesting than the ordered phase of an Ising model, no? So if you think of a Heisenberg, on this case, I guess for the purpose of illustration, I'm going to draw one where the sphere is just a circle. In this case, the model is usually called the XY model or the rotator model. A phenomenon that can happen is, well, the spins, which are now these arrows, they can rotate slowly. And this is in contrast to the Ising spins, which always have to flip by a finite amount of time. These can rotate slowly. And as a consequence, okay, I guess this picture is good enough. As a consequence, what happens is that if you look at the spin-spin correlation, say at for x and y at large distances, and beta large enough so that in the low temperature phase, well, to first order, they behave in a similar way as the Ising spins, in the sense that there's what is called long range order, so they align over long distances. But then the interesting part is the next order correction, where they have a power law behavior. And that brings this class of problems into the class of problems for which the renormalization group method is relevant. And that's sometimes it's called the spin wave or Goldstone picture. And so the renormalization group has, in fact, been applied to these kinds of problems. And again, let me put a picture. This is Balaban. It has been applied to these problems, but I think it's fair to say that this simpler solution would still be desirable. There's a sequence of a number of papers, I think it's about 10, which are very complicated, and the better understanding remains desirable. But and I think it's physically, this is a very interesting problem. You may in some sense it's less rich than the critical problem, but in other ways it's maybe more physically relevant, in the sense that there's a number of other problems of important physical significance, quantum versions of these models, superconductivity, etc., which have a similar picture behind them. Okay. And then, since I've discussed the critical temperature and low temperature, let me also say a few words about what can happen at high temperatures. So high temperatures, so here again, let me just mention a critical or a prototypical model in the spirit of the previous ones that are as simple to define as possible. And in this case, the simplest model to define would be the discrete Gaussian model in 2 dimensions. And again, it's defined exactly like the other models, with the only difference that spins now take values in all integers, not just in plus minus. So it's like an Ising model, except the spins are taking values in all integers. And there's a little caveat here, which I'm not going to discuss. Let's fix one of the spins to be 0, because otherwise this integral or the sum is not convergent. But I'm not going to. It's a technical aspect. And in this case, well, if at low temperature, so beta large, it behaves much like a low temperature Ising model. In this case, we would not describe the configuration as ordered, though one could, but it would typically rather be described as flat or localized. And one way to quantify this would be to say that the variance of spin differences remains bounded. And this is in contrast to what happens at high temperatures, which in this case is the interesting, or both regimes are interesting, but in this case, it's the regime where the renormalization group is relevant. In this case, we would say the model is in a rough phase or delocalized. So in this case, spins remain unbounded, and they divert. Spin correlations are unbounded, and they behave roughly logarithmically. So physically, this model is a toy model for a crystal interface, and this transition between rough and roughly localized, this is the roughening transition. Again, one can write down, as also in the Heisenberg model, but there I didn't write it down. Again, one can write down a Ginzburg-Landau version, which is kind of the phi-4 version of the discrete Gaussian model. In this case, this is called the Sine-Gordon model. And it's, again, there's a second parameter in this case, which controls the strength of the softening of the interaction. And for all physical purposes, we think of this model as completely equivalent to the first one. And again, I've scaled, as is customary here, to for a continuous model such that the first term doesn't have a coupling constant in it. Okay, so this. These models are also of interest for other reasons. It turns out that they're equivalent to the two-dimensional Coulomb gas. And in 3 dimensions, they turn out to be also related to abelian gauge theory. But I'm not going to go into this further. I just wanted to give examples of relevance of the renormalization group in rather different areas of the phase diagram. The above problems, they all discuss what one would call the infrared problem. So this is the problem of the statistical mechanical problem of what happens at long distances. But as I mentioned, this was, in some sense, I think, half of the class of problems that inspired the renormalization group. The other half are the problems that come from quantum field theory, and which here I would call continuum limits. So in this case, we're looking, say, at lambda epsilon, which is a scaled lattice. And as before, epsilon, we're thinking of epsilon goes to 0. And then in many cases, one can define versions of the models that I introduced before, but on this rescaled lattice. So formally, of course, you can just define the same models on the rescaled lattice by just rescaling the lattice. It turns out that if you want to take the limit epsilon to 0, you have to be a bit careful. And roughly speaking, this is what it is. So let me look at the simplest of these models, at least the simplest to define, which would be the phi-4 model. So it's like the lattice phi-4 model I introduced. In this case, well, we're looking at spin configurations on the rescaled lattice, so they're an R to the lambda epsilon. And we'd like to define them on the rescaled lattice. And well, what one should do is replace the sum by a Riemann sum. so that it becomes an integral. And then we'd like to define them, say, in the same way as before. Except you should also, in the Laplacian, also rescale it to a rescaled Laplacian, so that as epsilon goes to 0, this will effectively become the continuum Laplacian. So what you do is you have to rescale by epsilon to the -2. That would be the Laplacian. And then there's the same phi-4 potential as before, denoting the coupling constant by lambda instead of g for continuum. We can also put a mass term. I'm going to leave some space here. And I guess I'm using mu instead of nu for a continuum. And then that's in the exponential. And then we're integrating f of phi d phi. Now, so this would be just a naive adaptation of the lattice definition I gave before, except I changed the sum to Riemann sum. And now the goal is slightly different. We're interested in taking epsilon to 0 and defining a model on or a measure on continuous configurations. Turns out that if you do it the way I defined it, you will only get a what one would call a trivial measure, or you'll get a white noise or something like that. And it turns out to define a measure that is interesting, non-Gaussian, you need to put an additional term here. I'll denote by a epsilon of lambda. And that is what's called a divergent counter term. And it turns out that if you choose this a epsilon of lambda in a specific way, and it turns out there's a simple explicit choice you can make in dimensions 2 and 3, you will obtain a non-Gaussian measure. And we also know that in dimensions 4, you cannot do this. And in fact, this is a recent result of Hugo and Eisenman. But in dimensions 2 and 3, which I'll focus on here, you can do this. And what does it have to do with the renormalization group or with the picture of strong correlations? Well, we can again look at spin-spin correlations. And now it turns out at short distances, they behave like a power law. Okay. So in that sense, they fall into the same category of systems where there are strong correlations, now not at long distances, but at short distances. And you can look at versions of the other models I discussed. If you look at versions of the Heisenberg model, that is called the nonlinear sigma model, and it's particularly interesting in dimension 2. And you could go on. So this is and it turns out that these models are very so it's a different. It's sort of a different regime of these models, but they turn out to be very closely related to, in the phi-4 model, the critical case of, or near critical case of the Ising or lattice phi-4 models. The nonlinear sigma model would be more closely related to low temperature properties of the Heisenberg model. And okay, so this was a brief overview of models just in this relatively tractable and simple class of spin systems where strong correlations appear in various regions of the phase diagram, and where, as I'll try to explain in the remaining lectures, the renormalization group picture is for that reason relevant. At this point, let me just mention that, I mean, there's various other problems that you can look at. You can look at dynamics, deterministic or stochastic, where these ideas are important. You can look at more combinatorial models. such as self-voiding walks, the dimer configurations, etc. You can look at maybe quantum statistical physics models. Etc. A lot of and others. A lot of these problems have the feature that even though if you see it the first time, the class of lattice spin models looks like a somewhat restrictive class of models. If you allow a little bit of flexibility in the interpretation of these models, is actually an extremely rich and broad class of model that includes a rather vast range of phenomena and different types of models. But there are also models that, and in fact, many other kinds of models which at first seem unrelated can be sort of reduced to models like these. And that's, for example, the case for these examples of self-voiding walks or dimers and others. But there are also other models that they don't look exactly like this and where it'd be desirable, but not so much, there's been some progress on such models, but not so much is understood, I would say. I like, so maybe I can, before taking a 5-minute break, conclude with this other quote I extracted from one of Wilson's papers. It turns out he has a number of very nice papers with, if you're interested in a historical, why is this? Anyway, it doesn't want to move where it should be, but anyway, we can leave it here. He has a number of of nice papers where he discusses the historical aspects and the philosophy behind this approach. I linked some to the website. So here's one quote I like. This was in 1975, where he wrote, "It's at present an approach of last resort to be used only when all other approaches have been tried and discarded. The reason is it's rather difficult to formulate the renormalization group for new problems, etc." And then he concludes that it will probably require several years of stagnation in elementary particle theory before theorists will accept the inevitability of the renormalization group approach despite its difficulties. This was in 75. I think it's fair to say that by now it's unthinkable to think of much of modern theoretical physics without the renormalization group approach, and it may require several more years of stagnation in other areas as well for this. But anyway, let me leave this quote as it is, and maybe this would be a good time to take a short break, and then after the break, I will begin with more of the mechanics, which is the definition of the renormalized potential and some basics and background on Gaussian integrals, which are required to understand this.
Okay, great. Maybe to leave time for the people on site to have coffee, maybe we make a 10-minute break and we resume at 5.
Yeah, that sounds good.
Are we allowed to ask questions at this point?
Yes, of course. I mean, you are allowed to ask questions during the whole thing. You don't have to wait.
Okay,
yes,
thank you.
Yes, please do interrupt me at any point. Yeah.
So just a small question. When you were introducing a lot of these examples, you had a distinction between the ordered phase, the disordered phase, and the critical phase. Just to affirm, this is always with respect to equilibrium states, correct?
Yes, I've only focused on equilibrium here, and I will only focus on that during these lectures. Yes.
Okay, but then
yes, there's a very, I mean, the picture gets much richer if you add dynamics into it as well. But this is all equilibrium.
Okay, so actually that was my next question about the dynamics, because sometimes if you have stochastic dynamics, you might leave equilibrium. So you won't be considering that situation in your talks, correct?
I won't be considering that situation. It's a situation that I think is very interesting, but in fact, it's not very well understood mathematically. There can't do too much there.
I see. And in particular, do we understand how to define order and disorder in this context? Probably not yet, right? As like some kind of perturbation in the space of states or something like this?
Well, I am not sure.
Okay.
Yeah.
Okay, thank you.
So in this second half of the first lecture, I'm going to introduce some of the one of the main objects in the study of the renormalization group, which is the renormalized potential. And to do this, I need to discuss a few aspects of Gaussian integrals. So this is maybe 2.1. So first of all, in the way I wrote down these models previously, there was always a Gaussian factor, the nearest neighbor coupling, and some kind of interaction, which was either enforced by a constraint or by potential. And so it turns out that much of the renormalization group perspective is based on a detailed understanding of the Gaussian part as a reference. And so the Gaussian part is just what's known as the free field. So the expectation, if we drop all interaction, just be the free field. And in particular, it's the Gaussian measure, so it's completely determined in terms of its covariance, and its covariance is the two-point function, spin-spin correlation function, which in this case, maybe actually to make things a little bit more well-defined, I'm going to add another quadratic term, so-called mass term, and then the two-point function is simply the inverse of the Laplacian, or the Green's function. And so, of course, I think I'll not have to explain, but let me still summarize this, how the Green's function behaves, and say, I always like to think about a finite set lambda, and usually it'll be nice to take a torus, so periodic boundary conditions. And then we could ask, well, and then if you look at the Green's function in the infinite volume limit, and as the mass goes to 0, well, we know how it behaves, and this limit is like x to the d-2 in dimensions 3 and higher, and it's infinite in dimensions 2 and lower. And you can ask more precisely what happens in dimension 2, and if you subtract the divergent term, which is just the diagonal term, and take the same limit, well, then it behaves logarithmically in dimension 2 and linearly in dimension 1. And while all of these spin models I defined the first part of the lecture look like some kind of perturbations of a free field, it turns out they're rather singular perturbations. And a key difficulty is that, well, the Gaussian field they're at least formally perturbations of is a field that has these correlations I just wrote down. So they're very strong correlations. And it turns out the perturbations don't look very small if you do this. And that's what I'm going to try to explain. But it should be plausible from this that it may be useful to decompose these singularities or divergencies of the free field and look at what happens at one scale at a time. So you can decompose, you can imagine decomposing x to the minus d over minus 2 in various ways, and similarly for the log, etc. We want to do this at the level of the Gaussian reference measure. So let me just set up some notation for a Gaussian measure. So I'm going to use P subscript C for the Gaussian measure with covariance C. So it's the densities, maybe determinant 2 pi C to the minus 1/2. And then the density is minus 1/2 phi C inverse phi. And E superscript C will denote the corresponding expectation. So this is the integral of f of phi pc phi d phi. Now, there are another factors. Well, that if you have two Gaussian measures and you convolve them, you obtain another Gaussian measure. And the new Gaussian measure you obtain has the covariance, which is the sum of the two covariances. So if C is the sum of C1 plus C2, where C1 and C2 are all positive definite, not bigger than 2, bigger than 0, then PC is the convolution of PC1 and PC2. Or equivalently, you can do the expectation with respect to the Gaussian measure of covariance C by doing first the one with respect to C1 and then the one with respect to C2, say phi 1 plus phi 2. Now there's a little, I'm sweeping a subtlety under the rug here, since I usually talk about positive definite, meaning positive semi-definite, and the formulas I wrote down only make sense if it's positive definite, but that is easy to take care of, and I'm not going to do that here. This basic identity plays an important role. You can also do it continuously. So if you can write the covariance C as an integral of other covariances, CT dot, where the CT dots are now negative now, then, well, the convolution property becomes the heat equation. So it's the fact that if you have the Gaussian measure P with covariance CT, it satisfies a heat equation where it looks like this, where this Laplacian CT dot is a very high dimensional one. It's the sum over x, y, in lambda, c dot t, x, y. So that's the covariance, the xy element, the covariance matrix. And then there's the second derivative in direction phi x and phi y. And so this fact is just a straightforward generalization of the fact that if you have a Gaussian density, it satisfies a standard heat equation. If you put a covariance in that varies in time, this is the heat equation you get. Correspondingly, you can also have an analog of the iterated expectation property, which we may formulate now in the way that phi can in distribution be viewed as a stochastic integral. Where these dWs are Brownian motion on R to the lambda. And so this phi has distribution PC of the Gaussian measure. So these properties of decomposing Gaussian measures are in some sense the starting point for the quantitative understanding of the renormalization group, Wilson's spirit. We have a Gaussian reference measure, say the free field, and we can decompose it using this property. If we can write its covariance, which is the Green's function, as a sum of covariances or as an integral. And it turns out there's different ways to do this, and there's not one best way to do this. So question is how to decompose the free field. Let me write down a few different ways you can use. One of the most canonical ones would be what I would call the heat kernel decomposition. You can of course write the Green's function as an integral over heat kernels. So that is one way. There's other ways. Another one, which I call the Pauli-Villars decomposition, is you can write the Green's function as an integral over Green's functions with by varying the mass parameter. So we take the integral 0 to infinity of d dt of is Laplace plus m squared plus 1 over t dt. So explicitly, this is you can do other decomposition. You can do a block spin decomposition. I'm not going to write down what this is precisely. This is one. So all of these decompositions I wrote down are continuous. The block spin one isn't. It's sort of a it's a particular way you can decompose the Gaussian measure that is motivated by the Kardanoff block spin picture, and in some sense closely related to it. That was used, for example, in the work of Gewetsky and Kupiainen I cited earlier. So this is the block spin decomposition. You can use a certain decomposition, which I'll be talking about more later on, which is called a finite range decomposition. In which case we decompose the inverse of the Laplacian in terms of these matrices CT dot with the so that the CT dots have finite range property. CT dot xy is 0 if the distance between x and y is bigger than t. So note that the heat kernel so the heat kernels or the Green's functions and the Pauli-Villars decompositions, they all have approximate versions of this locality property, but not exact. So for example, for the heat kernel decomposition, you essentially have a Gaussian tail. But it turns out you can make this exactly 0. That has technical advantages. You can also use what I guess it would be called a momentum space decomposition.
Roland?
Yeah.
I'm maybe I'm a bit lost. I don't really understand why you need to introduce such a decomposition. So I agree that all these are decomposition of this resolvent, but it's not clear to me why you.
Yes, I will explain. I will explain this more. So in some sense, So we have this free field, and it has these correlations which are very singular, right? It has these singular correlations, and we're interested in studying perturbations of this. And it turns out that if you try to study, and this is what I'll explain this concretely, so I think things will become clearer then. If you try to understand, use this full Gaussian measure as a reference measure and look at perturbations of this, what you'll obtain is going to be extremely singular. You'll get divergent coefficients, and et cetera. So these are the infamous divergencies of quantum field theory. In some sense, the renormalization group picture, so these decompositions are sort of a proxy for Kardanov's block spin picture. Rather than looking at the whole system at once, we want to look at what happens at a single length scale. So say, what happens if you go from microscopic points to like blocks, and then from blocks to bigger blocks, and so on. And one way to do that would be to go from one length scale to another. You can do this continuously, as here, or in discrete steps. But as I'll explain, one way to achieve it is to start from a decomposition of the free field. Does that make a little bit sense?
Yeah.
So that's the motivation. Thank you. Please do ask at any point, because it's better to sort out questions as we go. So another way to do it is what one might call a momentum space decomposition, which has a kind of a finite range property in Fourier space. And so these are different ways you can decompose the reference free field. It turns out they all have different advantages, unfortunately. So, for example, the heat kernel decomposition has many nice properties. It has very fast decay, etc. But it also has a nice positivity property. For example, the heat kernel is pointwise positive, right? The Pauli-Villas decomposition has, it doesn't have such great decay. If you compare this to a heat kernel, it has a rather slow tail. And for that reason, it's not usually particularly good decomposition, but it has other good properties, which is that, determine the decomposition is a local operator, or it's the inverse of a local operator. And so in that sense, it often preserves the property of, say, the ferromagnetic property of spin systems, and others. So it has a locality property, which makes it has nice properties. The finite range, or the block spin picture or decomposition, has a nice property in the sense that it comes with an exact reduction of dimension. You go from single points to blocks, and so somehow the dimension of the problem gets reduced as you go on. I haven't explained what it is, but to take my word for this, the finite range decomposition has a nice compact support in real space property, and the last one has a nice compact support in Fourier space property. Now, it turns out, and it may sound a little bit silly if you haven't seen this before, but a lot of the technical difficulty of the renormalization group is related to the fact that these all have nice properties, but you can't have all the nice properties at once. So what I should emphasize is these decompositions, you can't do anything. You need to do something so that the term that appear in the integral or in the sum are positive definite. And that poses a constraint, a serious constraint of what you can do. So sort of a philosophically technical difficulty. different decompositions. Different advantages. And we don't know very well how to harness all of them. In fact, there is sorry. There's in fact a toy model you can define it, and a Hawk model you can define by just requiring that all 5 good properties hold simultaneously, and that model is called the hierarchical model. I think I'm not going to be talking about the hierarchical model in these lectures, but it's if you look at the renormalization group literature, this is an example that you'll encounter again and again, and I think one can characterize it uniquely to have all 5 good properties. Unfortunately, if you go away from the hierarchical model, you will lose some of these good properties, and you have to work around the others. You can keep some, but you have to work around the ones you lose. Okay, so we've looked briefly at how to decompose the free field. Now we can look at the renormalized potential. So we're interested in understanding the measure with expectation. I know by bracket I'm putting a subscript 0 now, which is of the form, say, Gaussian density with covariance C, and then some potential, which I'm now going to call V0. We've seen that, so the covariance is, the reference covariance is a free field covariance, and we've seen we can decompose it, and what we can also define is we can define a regularized version where we use the decomposition up to some varying scale parameter t. So instead of integrating up to infinity, I'm just integrating up to t. So that I'm going to call covariance decomposition. And then we can define, and this is sort of, well, one of the protagonists in the subject, it's called the renormalized potential, defining it through its exponentials. Vt is defined by just convolving the Gaussian measure with covariance Ct with respect to the exponential of the original potential. Or in other words, we're taking a Gaussian expectation with covariance Ct, and then we're looking at e to the minus v naught of phi plus zeta, where zeta denotes the field under this Gaussian expectation, and phi is fixed. And so this object is called the renormalized potential. So definition is very simple. So here are another few facts. Well, first of all, using the decomposition property of the Gaussian, or the convolution property for Gaussian measures, well, we know that e to the vt of phi, well, can be obtained by starting not with a potential at scale 0, v0, but instead by vs, and then convolving instead with the Gaussian measure with covariance ct minus cs. So this is like this. Or continuously e to the minus vt satisfies this heat equation. So let me recall again the notation and write out.
Sorry.
Yes.
I think the potential in the first line should be Vs.
Sorry.
The renormalized potential in the first line should be Vs instead of V0, right?
in the first line. Oh, thank you. Yes. Yes. So the exponential of the renormalized potential has a structurally very simple structure, the heat equation. If you take the logarithm of this, you can also check it satisfies a nice equation, and it's called the Polchinski equation. It's like a Hamilton-Jacobi type equation. So dv dt satisfies this Hamilton-Jacobi type equation. Let me just write out what exactly it means, just to get the notation. So the first term is the second derivative of vt with respect to phi x and phi y. The second term is and I guess at this point, there's another opportunity to put a picture. Let me just put a picture of Polchinski here. So this is a structurally very nice equation, and I'll try to convince you in this lecture that it's worth understanding how to study this VT, and in some sense, that's much of the problem, how to do this. Now, once you know, let's suppose we know what this VT is. Yes.
So, are you saying that on the finite lattice, all these formal manipulations are actually good?
Yes, everything's on a finite lattice. It makes perfect sense. The definitions are all completely. I mean, it's a finite. There's no problem defining any of this, right? Because we're on a finite lattice. The problem is how to get estimates that do not depend on the fact that the lattice is finite. Put it that way. But it's a very nice equation if we're on a finite lattice. So why is it useful to study this renormalized potential? Well, you can introduce another object which is the renormalized measure. Well, we would so our initial expectation was had a subscript 0 here. I'm now going to put a subscript t, and this is defined like the original measure, except we replace the potential by Vt, and we replace the Gaussian part by the Gaussian part that we haven't integrated or convolved into the potential. So that would be, instead of C infinity inverse, we put C infinity minus CT inverse here. And then we put Vt of phi instead of V0 of phi. So that one could call the renormalized measure, and whatever appears in the exponent is also called, you can give another name, Ht of phi. It's sometimes called the Wilson action. Maybe I'll move this. Next slide. Well, what do we do with this? So what do we do with this renormalized measure or with the Wilson action, assuming we can find it? In principle, we can find it whenever we're on a finite lattice, but suppose we can find it efficiently or quantitatively well. Well, ultimately, what we'd like to do, we'd like to compute, for example, a correlation function or other expectations with respect to the original measure. So we want to look at observables. So given an observable, say f, which is a function of spins, say like this, question is, can we find ft, renormalized version, such that the expectation of the observable f with respect to the full measure is equal to the expectation of ft with respect to the renormalized measure? And the answer is, once you know the renormalized potential, yes, we can. Maybe it's another fact or exercise. If we suppose that ft satisfies the following linearized version of the Polchinski equation. So LT is the linearization. Well, then you can check that the expectation of ft with respect to the renormalized potential doesn't depend on t. And since it's only one line, let me just do it. We want to check the derivative is 0. So what is the derivative? Well, up to a constant I didn't write above, but if we write it above, what we have is a Gaussian measure with covariance C infinity minus CT. And then we have the renormalized potential, e to the minus VT. And then we have the time evolving or scale evolving observable FT. I want to check this derivative is 0. Well, why is that? Well, the derivative can act on, well, either the first term or the second one. If it acts on the first term, well, it's a Gaussian measure with a t-dependent covariance, so it satisfies the heat equation. But actually, be careful, there's a minus in front of the term with a t, so it's a heat equation backwards in time if you want. So if you take the derivative of this, it's minus ct of pc infinity minus ct. If you look at the other term and take the t derivative, well, it turns out the definition of ft was just arranged in such a way that this satisfies forward in time heat equation. So the first term gives a backwards in time heat equation, the other one a forwards in time heat equation, but you can always integrate the Laplacian by parts, so you get the sum of two terms which are equal with a minus sign in between, so it's 0. And you can also write an explicit formula for ft, which is that ft is equal, so ft of phi is equal to e to the plus vt of phi. Just writing this down to illustrate that in principle, structurally, all of this structure is actually very nice and simple. And as you can see from the equation for ft, once you know the renormalized potential, it's a linear equation. And in fact, if you, for example, use the renormalization group in the spirit I will explain later, to study correlation, this kind of procedure is what one can do. It's often not written in the differential form here, where somehow it becomes a bit cleaner, but it's done in discrete steps for a reason I will explain. In principle, once you have the renormalized potential, you can study and have sufficient knowledge of it. You can study what you want, more or less. So anyway, the upshot is there's a nice structure.
Sure. So here at this
yes.
stage, you're deviating a little bit from the physics literature, as far as I can see, right? So
yeah, I mean, there you can. So I've in preparation, I've done some reading, and I also found some physics references which do essentially which look at essentially the same. But yeah, I mean.
But that's not kind of the central point of view. The central point of view would be to say, well, you just split phi into some part which you integrate out, and then you, yeah. So yeah, you would.
Yeah, I mean that's what I'm doing here, right? I just wanted to give some motivation or some perspective of why good understanding of the renormalized potential is very useful. And
actually, take it back. I think what you're doing is just a smart way of expressing what we do in physics anyway. So sorry, I take it back. It's
yeah,
I
think it's the same. Yeah,
okay,
I think it's the same. So anyway, there's a beautiful structure here, I think, and I hope I mean, and it's very simple, but the question is, how do we understand it? Maybe as a nice exercise, let me mention, so I've written an equation for the effective potential, or the renormalized potential, which is the Polchinski equation, but you can also derive equations for all sort of other objects appearing here, which are also somewhat nice. Maybe the Polchinski equation, my view, is the nicest of these, but you can write in the equation for the Wilson action, HT. In fact, this, I think, well, this appears in one of the earlier papers of Wilson for the renormalized measure, etc. So I've already mentioned the upshot. It's a beautiful structure. How do we analyze it? And before explaining some of this, there's a point I need to discuss, which I have swept under the rug so far, which is the topic of rescaling. So maybe it's a remark. If we go back to the Kardanoff picture I explained in the at the very beginning, I sort of motivated that, well, you start from points, you reblock them into blocks, and you think of an effective model defined on blocks, and then you iterate this, and somehow the blocks become the new proxies for the initial points. So you'd like to think of the blocks as the new point. So in some sense, you might want to rescale the blocks back to points, etc. In what I explained here, this decomposition of the Gaussian does provide a way that to approximately implement this block spin picture, in the sense that we can decompose this Gaussian measure according to one of these ways. Look at the renormalized potential, and in some sense, this renormalized potential is whatever the effective model at the level of the next blocks is, except I haven't insisted on really going from points to blocks. I've just insisted on, or I've replaced this with a substitute of changing what the Gaussian reference measure is. But you can think about it a little bit, and you realize that it's more or less the same thing, except it's done in a sort of analytically nicer way than. While this block spin procedure is intuitively very appealing, it's analytically not very nice to work with. And this is maybe a nicer way, but philosophically the same. The aspect I didn't discover or didn't discuss is the rescaling aspect. And so let me just say a few words about this. So the covariances, CT dot, so CT dot is, for example, a heat kernel, right? So they're approximately scale invariant. So if you're on the continuum, they're really scale invariant. We often like to start with a lattice, so then they only become scale invariant somehow as the limit, as t goes to infinity. You do some scaling. So the covariances CT are approximately scale invariant. If, say, CT dot is the heat kernel, then well, ct dot xy is roughly speaking something like this. Roughly speaking, a heat kernel. So you can rescale. So let's say I'm rescaling this parameter t, which I sometimes call time, but really it's better called scale, say by parameter L, and you scale x and y also by L. I'm rescaling scale by L squared here because I'm using the standard heat kernel parameterization, and then space has to be rescaled by L. And it's also good to rescale the measure we're integrating this heat kernel over, which is dt, which has to be rescaled by L squared. Well, then this is the same as L to the d minus 2 ct dot x y dt up to lattice effects, etc. So this c dot, which appeared in the Polchinski equation or elsewhere, is approximately scale invariant, and so it would be natural to add a rescaling procedure to the equations. So there are different philosophies about this. For different philosophies how to do this, I think. You can either add the rescaling explicitly, and for example, when Wilson writes down his equations, that's how it's done. And at some point, you need to look at rescaling. But the equations become nicer if you don't do it explicitly, say, as in Polchinski equation. There's no explicit rescaling. And one just imagines this potential you obtained, Vt, ultimately, everything should be maybe composed with a scaling map, but you don't write it down explicitly. I'm going to take this point of view here. And well, then once you take this point of view, it makes sense to ask about what are called renormalization group fixed points, or stationary solutions to the Polchinski equation up to rescaling, or let's say asymptotically stationary solution. And conceptually, this is a, I think, really important notion that the renormalization group idea of thinking about the problem introduces. So renormalization group fixed points should be, let's say, asymptotically stationary solutions let's say to the Polchinski equation or any of the other equivalent equations up to rescaling. And the picture, or I guess conjecture, or is that, for example, if you look at an Ising model in particular 3 dimensions, okay, let me discuss that in a second. Is that, well, you can have different fixed points. One is the fixed point, which would be just the free field, which in the Polchinski equation just corresponds to v equals 0. Surely that is a fixed point and a stationary solution to the free field, to the Polchinski equation, even up to rescaling if you rescale 0. But then, and the sort of the picture is that in dimensions above 4, this is essentially the only interesting one. There's also what is called the high temperature fixed point, but let me not discuss this much here. So the free field for critical phenomena is supposed to be the only one if you're in dimensions above 4. But in dimensions below 4, we expect there to be another one, which is called the Wilson-Fisher fixed point, and it appears exactly at dimension 4. So it appears in dimensions less than 4. The critical behavior of the 3-dimensional Ising model is supposed to be described by this Wilson-Fisher fixed point. And unfortunately, I'd love to, but unfortunately, I will not say much about this in these lectures, and especially not in dimension 3. But a concept that has been very instructive is to look at what happens as the dimension varies, not in terms of integers, but continuously. Well, to mathematicians, this is a concept that may sound a little bit not sure if frightening is the right word, but it's not the conventional thing to do. And in fact, there's different ways of trying to interpret what that's supposed to mean. One way to interpret it is, for example, replacing the Laplacian by fractional power. That has much of the effect of a fractional dimension, even if I would say not the complete one. But okay, let me not go into this and only mention that if you do this in some way or the other, the distance between these two fixed points is supposed to be of order 4 minus d, the positive part. So if the dimension is 4, both fixed points merge into 1. So above 4 dimensions, there's only the free field fixed point left. In 4 dimensions, there's exactly 4 dimensions, there's a bifurcation point where the two fixed points come together, and you can see this in various properties of the 4-dimensional model, which is the critical dimension for these models, in terms of so-called logarithmic corrections. And if you go below 4 dimensions, well, you see the new fixed point appearing, and in particular, it's supposed to be there in 3 dimensions. And so this is another opportunity to insert a picture. Let's see where he is. I mentioned this is called the Wilson-Fisher fixed point. I've already had a picture of Wilson. This is Michael Fisher. Who studied this picture with Wilson. And to be honest, to be clear, this is, I mean, for dimension close to 4, slightly below 4, there are certain things one can do mathematically. But I think in general, understanding the robustness of this picture and the beauty with it remains mostly elusive. Okay. So much for that.
Question.
Yes.
Yeah. I guess the Wilson-Fisher fixed point represents something like the behavior at the point of phase transition.
Yes.
Description.
Yes.
So that's the point of view from statistical physics. What does it represent from the point of view of Q of t, i.e. the UV limit?
Well, it's for the UV limit, the one you see is the free field fixed point. So it's not really it's the free field fixed point is the one that is in dimensions 2 and 3 that is stable for the UV. Yeah. I mean, you can, yeah. Okay. Yes. So what I want. Yes.
One question. What is this notion of distance you mentioned?
Well,
what do you consider the distance?
Well, I mean, okay. So this is something I will not explain in these lectures. I just wanted to mention it because I think, I mean, it's important and to get some, to discuss the idea of this renormalization group picture. But well, what you can do in perturbation theory, which is the topic I'm going to discuss beginning with the next lecture, you can write down these approximate versions of the so-called flow equations, how the effective potentials changes as you change scale. And what you see is if you do this in dimension 4 minus epsilon in a suitable way, and for example, by replacing the Laplacian by a fractional power, you can write down these equations, say for 5-4 type models. And what you see is that in 4 dimensions, at least this perturbative way, you can only see the free field fixed point. But if you go to dimension 4 minus epsilon, you see there's a new fixed point appearing in these equations. So this is essentially, at this point, it's a computation at the level of a single variable. It's a single coupling constant where you can write down this approximate equation for, and you see the parameter epsilon appears, and in some sense, the location of this fixed point, the Gaussian fixed point is at 0 in this setup, and the non-Gaussian one will be at a coupling constant which is close to 0 for the epsilon. I'm not sure if that was a convincing answer, but I'm afraid this is as much about this as I can say in these lectures, or as I'm going to say, because I want to focus on other aspects that this is an interesting aspect, and it's one aspect one could focus on, but there's many other things to discuss in somewhat conceptually simpler contexts where the technical machinery or ingredients are very much the same, but I focus on a simpler setting. Okay. So next time, what I'm going to do is I'm going to explain how perturbation theory works, because that's sort of the main guideline, how to get understanding of the renormalized potential. So I think this, I think this might be a good point to stop for today and resume there next time. This is a logical division, and so maybe let me do that. Thank you for your attention.